the second phase. You know, some might call this as the first phase of the loop, technically. This is where the loop actually starts, right? Because the initial phase was just loading the main module and then an initial phase and then maybe loading modules and executing any synchronous code there. And you're just like going one by one, right? But now we're actually in the loop that this phase is gonna be executed over and over and over and over again, as long as there are timers, of course. You know, before we actually dive into this, I just want to let you know that to take a breath and try to explain just how timers actually work, right? How would you tell the OS, hey, execute this code after 5 seconds? You know, the only way, we have two methods that I know of, at least, right, to achieve that. And you might come up with a third. The first approach, well, let's call it three. The first one is actually not very optimal, but let's say it's one way to do it, right? But don't do it. That's not a good idea. You have a process and you say, hey, I want this process to execute this code after 5 seconds. So what you do is you do a start timer, and then you do a loop, and you check, has it been 5 seconds yet? 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 And then once it's been 5 seconds, you break the loop, and then you exit, and then you execute your code. And it will be as if it happened after 5 seconds, right? That's a bad idea because you're just wasting energy and you're actually having the CPU execute nothing, right? Because you're looping, you're waiting, you're checking. So the other approach is, so almost no one uses that approach, right? The other approach that is actually being used today in Node is to ask the OS to sleep. There is a system called sleep, and it's almost 90% accurate, 95% accurate. It will say, hey, sleep me. I am a process, just make me sleep for 5 seconds, 10 seconds, 30 milliseconds. And it knows that kernel is always running and watching. It's like, oh, has it been 5 seconds? Like, or because it's doing its thing, right? Oh, this guy has asked us to sleep for 5 seconds. It has been 5 seconds, or maybe a little bit later more. And that is not accurate because the kernel might be executing things. It might be busy. It might be some delays. You know, an interrupt might happen, a hardware interrupt that can delay things. And if we forgot to wake you up as a process, and waking up a process is basically rescheduling it in the CPU. And that's why you guys, you have to take the OS course, right? Just take a break and take the OS course, because I talk about all this context switching of threads and stuff like that, right? If you're interested, if you're not interested to know more about that, that's fine, right? But yeah, it will just schedule it back. Sleep is nothing but, hey, take you away of that process and throw you somewhere else. Essentially, no, you don't have any code to execute, so I'm gonna put you to sleep, literally, and then wake you up, i.e., hey, you can now execute your necessary instructions right here, and that's basically putting you back in the CPU and context scheduler. So there is a little bit of a delay, but it's way more accurate, right, and efficient, because the kernel is executing them. So now when you wake up, hey, I'm awake, execute your code. And that's what Node uses today with using this library that's called libuv, right? And of course, not the main process of Node actually execute that. It doesn't sleep. Otherwise, the rest of our code will be put to sleep as well. No, we have other stuff. Node is asynchronous. We need to execute other stuff. So the sleeping thread is actually one of the libuv's thread. It's just one thread that sleeps, and it wakes up and it checks, hey, are there any timers, right? And that's the trick, using sleep. And the third approach, which is way more accurate, is using a hardware interrupt timer, which is the most accurate. Like an actual hardware that just Dang! Like when it's very accurate, precise, and that's the only job of this hardware controller is for to do timers, right? And it will do it identically. And I don't know much details about that, to be honest, right? But that's the three approaches we have. Now, with that in mind, let's get into the timer phase. Initial phase, done. Now the first phase is timers. Yes, sir. We're doing some timers here. This is where we execute, and then there's some stuff after that we're gonna run through. Okay. So right after the initial phase, this is where the event main loop actually get initialized. And the first phase are timers. Are there any timers? Ready? Let's execute them. If there are not, we move to the next phase. It's as simple as it is, right? And it's I kind of talk about this a little bit. It's done by this underlining library that's called libuv, right? Timer callback gets scheduled, sorted by duration. And here's the trick. This is the trick, really, right? Every timer that gets registered, we have a duration, right? When do we wake you up? Essentially, when is this elapsed? And they are sorted by this duration from the smaller to the largest. And what we do is we really sleep. We sleep in the shortest duration. And when we wake up, we check the rest of them. It's like, okay, I just woke up because you need to execute the soonest. But yeah, as we said, it's not accurate. Not only can be slowed down by the operating system itself, but it can be slowed down by other phases, like we saw with the initial phase, right? It slowed down our timers. I saw, hey, execute this after 1 millisecond, but it executed after 5 seconds. So I tried my best to explain this with a diagram, but hopefully I nail it with you guys. Let me know if this makes sense. So assume we have 3 timers that get scheduled at T0, right? Assume T0 is like, I don't know, 9 o'clock at the evening, something like that. Right? I use T0 because it's easier to ration about. But the timer is, the first timer is 100 milliseconds, the second is 500 milliseconds, the third is 950 milliseconds, okay? And they all get scheduled at the same time. Boom, 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 boom. Same time as the same moment, they are registered right now in the initial phase, let's say, right? And they say boom, 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 100, 500, 950. So what we really persist in the timer libuv metadata is the end time, not the start time, right? So when we say, hey, 9 o'clock plus 100 milliseconds, 9 o'clock plus 500 milliseconds, 9 o'clock plus 950. So T0 plus 100, T0 plus 500, T0 is 950. So at the end of the day, this timer should be executed at T100, right? And this timer should be executed at T500, and this should be executed at T5 950. So that's what's happening. We're persisting the end time. So what does the libuv does? Remember, it has only one thread for the timers. Just that's it, right? We're not gonna use multiple threads. We try to be efficient, right? So who do we sleep as, right? So these are my threads. So what we do is we sleep at the least amount of time, which is 100, 500, 950. Pick the least. Let's sleep for 100 milliseconds, assuming we started the timer phase right there and there at T0, right? If we started at T1, then we're gonna sleep at 100 minus 1. Does that make sense? So 99 milliseconds. You really remember, it's always like you preset the end time, right? How much time do you sleep is basically the current time, the destination time, the final time minus T0 minus the current time. So we sleep at 100 milliseconds. That's all. Boom, sleep and move on. So 100 milliseconds later, the OS will wakes up the thread, and the libuv thread will wakes up and says, all right, I'm wake up. Let me check all my timers. This is T100 millisecond. It's now T100, T100. And this is T100. All right, this callback's ready. Let me check this. T500 minus T100. Because you really do a minus, right? T100 millisecond minus T100. That's it. It's 0 or less, right? So let's say we woke up at 105, right? We woke up at 105, and instead the OS got delayed by 5 milliseconds, and we woke up at T105, right? So you minus 1, you would deduct 100 from the current time, and you'll see it's minus 5. So we have, not only this timer is actually it's delayed by 5 milliseconds, so it's ready. So we execute that, and we do the same thing. 500 minus 100. No, we still have 400 milliseconds left. So this timer is not ready yet. 950 minus 100. No, we still have another 850 milliseconds. So this is not ready yet. So we start executing the callback for T100 millisecond, whatever that callback happened to be, right? Boom, execute that. And now we need to sleep again. So what we do is, what do we sleep as? We need to sleep for the next least, which is 500 milliseconds. But guess what? We're not going to sleep for 500 milliseconds, right? Because if you sleep for 500 milliseconds, then that's wrong. You're gonna be delayed even further, because 100 milliseconds already passed. So you really sleep for 500 minus 100, and to be more even exact, 500 minus whatever the current time is, because guess what? The callback is gonna take time. It's not gonna be free, right? So let's say you executed the callback, and then technically this whole thing happens in the libuv. So the main loop should not be the cost of the main loop shouldn't affect the timer of the timer libuv. These are two different threads, right? So libuv just moves on. So for simplicity, let's say 500 minus 100. So we sleep again for only 400 milliseconds, right? It can make sense, right? I'm sleeping for 400 milliseconds because that will wake me up exactly at T500, because 400 plus 100 gives you T500. And now I'm awake again. Let's say I woke exactly at T500 or a little bit later. You're not going to be awakened before that. It's impossible, right? The OS just knows that you don't wake away before. It's always after, right? You might be delayed, but you're not going to be earlier, right? That's what they guarantee the OS does, the sleep at least function. So we wake up, we execute this call, and then we're done with the T500. But now we have another timer. Is it ready to be executed? Well, let's see. 950 minus 500. No, we still have 350 left. Is it 350? 450, sorry. 450 milliseconds left. So this timer is not ready. So now we need to sleep again for not 950, right? We need to sleep for the remainder. This is scheduled to be running in 950 millisecond. Nice minus 500, right? And that gives you 450 millisecond. Now sleep for that 450 millisecond, and then we're going to be waked up into 950 or later, and that will just go through that. This is the actual implementation of how Node and libuv actually implements this stuff, right? You might not be interested in that. Some of you might, but that's how you write code. At the end of this, it's all code, and all based on the sleep, right? Some of you might say, I want a more accurate timer, and you can hook this up somehow, write your own libuv that reads a hardware controller timer and give a more accurate timer. But you'll have to change the Node.js implementation, because the phase itself, phases might delay timers, right? Because even that the callback is ready, all what libuv does is just marks this as ready. That's all what it does. So Node, when it comes in the timer phase, it just picks up the green ones, right? Because sometimes you can schedule like 100 millisecond and 101 millisecond, and somehow you got delayed by 3, 4, 5 milliseconds. So you pick up both callbacks and execute it at the same time in the same phase. Yeah. So that's basically how it works. So, all right. So what is the output for all this stuff? So this is another interesting thing. So what I have here is a timer callback that takes a function AB, right? You can, because in the timer you can submit arguments, which is amazing, right? And it can you can do interesting things with it, right? So A and B, and I have console, and I'm printing the value of A, timer callback, just the name of the callback, and I want to be like by how much are we delayed? How did I figure that out? Basically, the current time minus the start time at the initial phase. I just took a snapshot of the start time there, and then I'm gonna divide this minus start minus B. What is B exactly? B is the actual duration for the time, right? So let's say this is 100 millisecond. I just passed 100 milliseconds. 0, I just passed 0. So 6,000, I passed 6,000. And then because this minus this is just the start and the end time. And that's the time where we called the callback. And this is the time that we started when we register the callback. This time is the time where we actually called the callback, right? So if I do this minus this will give us supposedly the time for the timer, but it's not always the case. This should equal to B, but you will see that it's almost never the case. They will never be equal, because this is always going to be greater than B, because you're going to always be delayed by something, right? So I'm going to make a loop here to force the delay, and you can see that the timer 0 callback was executed first, and it was delayed by 385 milliseconds. That tells me that this loop actually took 385 milliseconds. And then this 387 millisecond, 289, 89, and by 2 milliseconds is the 6,000 one, because this is like a delayed timer, right? But look at all of them. All of them are actually more than 0. Okay. All right, let's go through. This is the summary, right? Runs after the initial phase, the timers. This is all implemented using the libov library. We went through a detailed implementation of how this is actually done. Timer callback gets scheduled, sorted by duration, and other phases can slow it down. Indeed, like we just saw actually an example here. And let's go through a code exercise, you guys. All right, let's do some example, you guys, here. So, okay, so this is the timer example. This is the same example that we had in the slides. Essentially, what we do is we take this value, we print it, and we just capture how much delay did we get. And I'm looping for 1 billion here, all right, just to see. This fluctuates. I say here 380 milliseconds, but it really depends on the time of the day, right? And how fast my machine is, and it depends so much. So feel free to change this value if it's too slow for you or too fast, right? So I'm just gonna do 02 timers and 020. You can see that timer, the 0 millisecond timer, right, got delayed by 318 millisecond, right? Because that's the closest one for us, right? It was supposed to execute right away, right? Now it should execute immediately, right? Technically, if I don't have anything, but executed after that. This executed after 1 millisecond, but we're delayed by 321. The 100 millisecond one is 222 milliseconds delayed, not much. And the 300 millisecond was delayed by 22 millisecond. All right, so you can see that timers are great, but they are not accurate. Right? So it all depends on when they are getting executed, and you can play with these values. This code is available for you. Let's do the second one. Timer 1 long. looks like it's yeah, it's the same thing, the same example, but I'm adding an extra time here where there is like a 6,000 number here. 6,000 seconds, milliseconds. So let's go ahead and run the second one. Not much difference here. Whoop. You can see the 6 milliseconds, 6 seconds waiting with the time, and you are delayed by 2 milliseconds, right? There's always some sort of a delay, and in your machine might be, and I've seen sometimes I get -1 in certain cases because there's like so much stuff going on here, right? There's the date.now, there's the time, there's a chance that my process has been scheduled out of the core. So all of this, take all of this with a grain of salt when it comes to these numbers. But they essentially tells us that here's the timer. We're playing with the timers. It has different durations, but it's damn accurate as long as you don't delay it. So let's go ahead and remove the delay and see what happens, right? Let's just remove the delay altogether. You can see that. You're still getting tiny bit of a delay, 1 millisecond, 6 millisecond, 1, right? But it's not as bad as 300 millisecond. So it's always good idea to check that at your end and see what is going on. Like if you have timers, see how long did the timer actually delay, because while you think you can trust the timer, there is always sometimes the chance that the timer has been delayed by so much unexpected factors, like especially when other read operations happen and you have like a expensive synchronous call in the initial phase or the poll phase or other phases. And it's just play with that. Find your code you have that has a timer and just add this piece of code to it. And see, it's like, this code this timer was supposed to execute here, but it delayed. And you might have been expecting the timer to execute after a second, but it delayed by a 3 or 4 second. And that delay caused a query to not be sent at the correct time, which causes a race condition with a colliding with another race condition with another query that caused, I don't know, some corruption. So good luck following that, that thread if that happens, right? But if you have the telemetry in this particular case, you can at least guess what could happen, right? Some benign things like timers that you think will execute, like, hey, I want to always execute after 5 seconds. That's another example, actually, right? Like, hey, I want a timer that always execute after a second. How do you do that? Well, you do a timer and then you schedule it. When the callback comes back, you schedule it again for another second. That's how I would implement it. But even that is not accurate. You know what? Let's just build it right now. Live, you guys. Right? 022 timer 1 second every, something like that. Okay, and then I will just do this. Right? Let's keep the loop. And we're doing multiple statements, so we need this curly braces. Yes, sir. We don't. What is this? Oh, this is the console log one. Close it. Yeah, let's close this so you can see the whole page, huh? Yes, so let's do that, and I'm literally gonna do that. Right? That's how we're gonna do it, right? Like every time, just execute it. And let's run it. Oops. That's it. Of course, that start time is now pointless. Like you can remove that delayed by, because it's kind of doesn't make any sense now anymore. But time, we can just do, or actually, we can do something like that. Good. Let's make it a let, and we do it every time, right? That's gonna make sense now. Let's see this. Yeah, because you need to do a start every time. Yeah, that kind of makes sense now. Okay, so what I did is I reset the start time every single time, right? Every time I'm capturing the new start time. So that's a perfect example. This is something this is a common example. I see. I did this once in a chatting app where I'm trying to poll something, right? And I did a timer for that. Not a great idea, but it's just something I did. And yeah, if that timer got delayed by any reason, you might delay the callback. If the callback is delayed, what will happen? You will not execute the callback execution in the time you expected, and as a result, unexpected result might happen. So keep that in mind while you're coding. All right, guys, that was the timer phase. Let's move to the next one.